Hi, this is Shane Mueller, and this is a screencast of Chapter 18 of the course, Advanced Statistical Analysis in Psychology and Human Factors. And today we're going to be looking at factorial ANOVA, including interactions. So previously we looked at one-way ANOVA and multi-way, meaning multiple predictors, but only looking at main effects. Now we're going to look at interactions. All the material for the course can be found at this website, including the course book, and we're on Chapter 18. And so if you follow this link, you can get the code that we're walking through and follow along with it. And let me back up just a little bit, because we had, I think in this previous chapter, we looked at the tooth growth data and spent, if I can go back without going too far back here. So we can see that in this data set it was measuring the growth of guinea pig teeth based on different dosages and different supplements. And before we had just modeled this as two independent effects, but as you can see, there's what looks like an interaction, at least, in that there is no difference here, but there is a difference here, and there is a difference here. And so if we have just a linear model with multiple predictors, we get parallel effects that look like this, that are going to miss this, and underestimate this effect, overestimate this effect, because it's going to sort of try to split the difference. And in order to incorporate this type of phenomena, you need what's known as an interaction. And an interaction, if it were just a two-way interaction, it's going to be you're going to be able to take these predictors, and there's going to be contrast to the predictors, and the R code will generate an orthogonal prediction based on the pair of these. So here it's going to take however these are coded and find the difference between these two and the difference between these two, and subtract that difference from that difference. And so if you just have a 2 by 2, you can see how combining them both, you can create an orthogonal predictor that allows for differences between these differences. So the size of the interaction is really this difference minus this difference, and you can get that by making a formula of the contrasts that based on which these are coded. If you have 3 and 2, there's other schemes for creating that orthogonal contrast set of contrast vectors for this interaction. And we won't go into detail about how those are coded, because when they're presented to you at the end, it's pretty easy to interpret, or it's at least reasonably easy to interpret. But just suffice to say that instead of using a categorical predictor or 2 categorical predictors, we're then also going to combine them together into an interaction that is going to be independent from either main effect, to allow us to capture differences in this size. Differences in the size of the effect that depend on one or another levels of the variables. Okay, so zoom back out. And here's just the same data we saw before. I'll bring the R code here. And I've opened up the walkthrough code for Chapter 18. Let me set the session. Okay, there we go. So previously, to make a regression model, we had just done something like this. We'd taken supplement, and again, now we're using dose as a factor in this tooth growth data. And now to make an interaction, there's 2 ways you can do it, which are sometimes a little different well, they're different. They're a little different. Sometimes they're a lot different, but sometimes they're basically the same model. If you just want to have that interaction term there alone, you use the colon. So you could add the interaction term to the main effects by saying sup plus as factor dose plus sup colon as factor dose. It's more common because of the way these models are framed to want to include both supplement, dose as main effects and their interaction, and that's what this syntax does. So the main difference is this includes just the interaction, and this includes the main effects plus the interaction. So if we look at TG2, you can see it lays out supplement, dose, supplement, and dose. And if we do TG3, well, now it's kind of curious that the residuals are identical, and the degrees of freedom, residual degrees of freedom are identical, and all of the sum of scores you're accounting for is sort of accounted for in a single term instead of divvied up between main effects and interactions. So the same pattern is accounted for in either of these. It's just that this one sort of divvies it up in a way that may make sense. And so you should think about whether this main effects make sense. And there's good arguments that a lot of times in the face of an interaction, the main effects really don't make sense. For example, if you have a crossover interaction where under one level of a condition you see a positive difference between two levels of another, and under another level that you see a negative difference and they cancel out, what's the main effect of that? Well, the main effect depends on the level of the other, so there really isn't a sense that you have a main effect. You only really have the interaction. But there's sometimes when it does make sense to think about a main effect, like if you've got between two conditions, let's say you have two training conditions and you look at the first day, and training condition 1 is has a score of 10 and training condition 2 has a score of 5. And you look at the second day, and training condition 2 has a score of 110, and training condition 1 has a score of 105. There's an interaction there because at the first day 2 was lower and the second day 2 is higher, but overall there's a huge learning effect as well. And in that case, it might make sense to talk about the main effect of learning of day plus the interaction between day and learning style or learning method. But in that case, it may not make sense to talk about the main effect of learning method because you see sort of it cancels out over the 2 days. Anyway, so you can frame an interaction model either of these ways, and it just sort of depends on which factors map onto your hypotheses. And as always, in an ANOVA model or a regression model, you shouldn't be thinking about just what's the standard way of doing this. You should be thinking about what are my hypotheses and how do I frame the model to test my hypotheses. Okay, so if I look at the summary of these, here's a summary of the main effects model, which we looked at before. And this is good to check. Supplement has 1 degree of freedom. That means it has 2 levels, and that was true. As factor dose has 2 degrees of freedom, which means it has 3 levels. We see that they're both significant in their main effects. And I guess we want to look at TG2. And now we can ask what is the effect of this interaction, and it's significant, at a 0.02 level. So this might be considered statistically significant. But it also gives you these main effects, and it sort of says supplement's significant and dose is significant and the interaction is significant. However, it's not clear what this means. Remember, we're always in a ANOVA model like this, we're always testing comparisons between models. So what is this supplement? Is this the comparison of the model with supplement to the model without supplement, or the model with supplement and dose to the model with just dose? Or is it the model with supplement, dose, and the interaction to just the model with dose and the interaction? That's not clear from just doing this, and that's one of the issues we'll be talking about today. If you compare that to TG3, all of these 3 effects are wrapped up into a single effect with 5 levels. And so you can kind of think what it's really doing is turning 2 main effects in an interaction into a 6-way, like a 1-way ANOVA with 6 levels. There's sort of 6 different, a pattern of 6 points, and it's sort of turning this into 6 different levels. And it's saying there is something different overall in that whole 6-level pattern. So this one on its own might not really test what you're interested in if you're interested in the interaction, because this could be significant even if you only had main effects that were significant. So probably what you're interested in is some test of the sum of squares that are responsible for this interaction in comparison to the whole model, if you want to test the interaction, or in comparison to the residuals left by taking these other things out of the model. All right, so that's the basic idea of framing and looking at an interaction. And really, if you don't know what this particular summary is testing, you can always build specific models and compare them. So I could say, well, I really want to know what the effect of this interaction is in comparison to just the main effects. So I could do TG3 and TG1, and you can see that I get an F-score of 4.1, a p-value of 0.02, and that's going to be exactly the same number that's coming up here. So that you can verify that what that's doing is that particular test. But when you have an interaction, it's unclear what this is or what this is, because this supplement here, the sum of squares is the same here. The F value is different. Dose, it's accounting for the same sum of squares, but again, the F value is different. So we'd like to figure out what the right thing to do here in these cases is. We could sort of build this into the model, so we could ask to do a summary of the regression model as you have these pieces versus these pieces, so just the times versus the colon. And you can see that if you look at this, the underlying way it's divvying these things up, including the intercept, the effect of supplement, the effect of all these things, change depending on how I build this. If I just have this interaction versus if I have it broken into main effect plus interaction. So really the underlying way the model is framed is going to change. But if we then do, as we saw by doing the summary of these, the overall effect of whether the whole thing is significant stays the same. Another thing you can do with one of these models is use the model.tables function. And this, it doesn't give you the coefficients, but this gives you the model's predictions about every level. So now you can see, well, this is the effects table. So this says, ignoring the intercept, the OJ versus VC will be plus or minus 1.85. So this is, so if you take the grand mean, you can make all these predictions based off the grand mean. If you look at dose, you have 3 levels of dosage, and if you add all these 3 things up, they'll equal 0. And you can see if you take the grand mean, level 1 is 0.92 higher, level 2 is 7.2 higher, and level 0.5 is 8.2 lower. And then this is the interaction is, and you can see the pattern here that that it just overlays a template on top of all of these and says, well, the interaction we see about a 1.5, that's 0.77 times 2 difference here. We see 1.1 times 2, which is 2.23 difference here, and we see a 1.89, which is, I don't know, 3.9, 3.8 difference here. But the signs differ, so if these were all the same sign, that would be the same as this, but you have the ability to change the sign between these two and this guy, and you could have changed the sign another way and then the coefficients would have all just adjusted to map, but you see it's a negative and a positive difference, two positive differences and a negative difference, which kind of measure that interaction, the magnitude of that interaction. There's another way to, you could look at that for the other one, and let's see. Here, it doesn't divvy it up between these main effects. It just gives me the overall interaction from the mean, the overall difference from the mean, rather than having to add up these and divide these. So this sort of is another way of looking at the difference between just including this interaction and including the times interaction. All right, so you can also use model tables to get the actual means. So they look slightly different in this case, but if I ask for the means, the model tables will take the model and give me the actual absolute numbers for each of these rather than relative to the grand mean. And now it'll say 18.8, 20.6, 16.9. It'll give me the mean of each of these, and then it'll give me sort of the mean of each of the 4 levels in the model. And if I do this, it won't give me any of this early stuff because I didn't include those as predictors directly. But these 6 levels will be identical. So you can see that whether or not you frame these as two main effects in an interaction or just the interaction, it's essentially the same. You're accounting for the same complexity of the model. You're just divvying it up in different ways. All right. And the next example we want to talk about is what happens when you how do you frame this lattice, this model lattice that we talked about in the previous chapter. And I think I'm trying to find it in the textbook. So again, we have this model lattice that has all possible submodels, but instead of calling the interaction A colon B, really it's a third independent variable that's independent of A and B, but has a special relation to A and B. And so let's just create that and call it C. So we'll have a separate variable we call C, which happens to be the interaction, and then we can think of this as just a factorial ANOVA without interactions. And a normal ANOVA model using the lowercase ANOVA built into R will report sets of sums of squares that look like this green line. So if you say A plus B plus C, we'll first compare A to the intercept only model, and then B to the AB model, or A and B in the intercept to the A and intercept model. And then it'll compare A, B, and C, the model with the interaction to the main effects without the interaction. So that's usually not what you want. You don't really want to compare A to only the intercept because there's other stuff going on there. And so before we talked about this type 2 and type 3 ANOVA, which if you don't have interactions I think are the same, but when you have interactions there's different things you could do. And both make sense. There's a type 2 ANOVA, which is this one. So let's see what one's doing. This one says, when I test the effect of A, I want to compare the model with A and B to the model with just B. So if I don't have any interactions and I only have A and B, that's the right model to do. And if I want to test the effect of B, I'm going to look at the model with just A and B and compare it to the effect of the model with just A. So that's the difference of B. So this is called the type 2 ANOVA. And then if you want to test the interaction, you test the model with A and B to the model with A, B, and the interaction. So that makes sense. This is sort of a reasonable thing to do to test the main effects against one another and then the interaction. Although there's another reasonable thing to do, which is to say, I want to test I want to test A to the model with to test A, I want to test the model with A, B, and the interaction, and compare it to the model with just B and the interaction. Now, this is kind of weird. One of the reasons people don't like it is because it incorporates this interaction even though you haven't tested the main effect yet. Similarly, B, you would test the model with A, B, and the interaction to the model with just A and the interaction. So this is called the type 3 ANOVA, and just like we talked about, sometimes the main effects don't make sense in the context of an interaction. These might be really what you're interested in, these comparisons. You want the effect of B only after you consider the interaction, because if there is an interaction, the main effect may not really make sense. That interaction is a complex pattern, and it may not make sense to think about the main effect until you've canceled out all of the interaction elements. So the issue here is deciding between type 1, which is probably wrong, this is rarely what you want, type 2, which may be what you want, but notice that you're testing A only in the context of AB and B only in the context of AB. Or on this type 3, which tests each main effect in the context of the interaction. So that's a choice you have to make. And a lot of these type 2 and type 3 ANOVAs are available within the car library's ANOVA function with a capital A. And by default, it uses the type 2. That's this one. And there's a couple of reasons for this. This is often what you mean. It's not always what you mean. It may make sense to only look at the main effects in the context of the interaction, and if that's the case, you should think about the type 3. But the other problem is that the type 3 has some problems when you're thinking about the model, in that what they say is it violates marginality. And this has related to the orthogonality of the factors. And so what you have to be careful about is, if you want to do one of these tests, you have to make sure that the contrasts of the factors are coded in a way that are orthogonal. And treatment coding is not orthogonal, or it's not balanced. So treatment coding won't do this. So you have to recode A and B with a different set of contrasts, and they recommend you could do Helmholtz coding, or you could do polynomial coding, which permit this. So you have to think about what are the comparisons I want to make. But if I decide that the type 3 ANOVA is the right type, then I've got to change the contrasts. And it's not actually that difficult to think about which one is the one I need. Here, if you want to do type 3, you're really asking, is there still an effect of that main predictor once its interaction with the other one has been accounted for? And there may be, that may be reasonable to ask in some contexts, but in other contexts it might not be reasonable to ask. So you have to kind of consider which of these to do. By default, Fox's car libraries, ANOVA uses type 2, and it's sort of the easiest to get right, and it's often what you mean. So that's sort of what most people recommend you do as a default. Use a type 2 ANOVA. Okay, so that's how these different types of ANOVAs interact with interactions. We're going to look at this in a sort of a worked example, and the context is fake data for something called the Ultimatum Game. This is sort of a game theory game where you play with a partner, and you, if you're the dictator, decide. You start like 10 coins, and they say, how many coins do you want to keep, and how many coins do you want to share with your partner? And you can decide anywhere between keeping them all or giving them all to your partner. And then your partner, the only choice they have is whether to accept or decline the offer. And so if they accept it, you each keep how much ever the first person decides. And if you decline, then nobody gets anything. So this is one of these paradox games, because the rational thing for the dictator to do is keep as much money as possible and give as little money to the partner. And what the partner should always do is accept whatever they're given, unless it's zero, because it's better than doing nothing. You'll always get a little bit of money if you accept. And generally these are in one-shot games, so it's not like you are repeating this multiple times. You're just doing it once, and so whatever you get, you keep. So here's a game that it's data, the sort of fake data that you might consider, and you can use it to think about how much money people would give based on their partner, what they know about their partner. And generally what people do is they give about half, and generally people reject offers unless they're around half. If they're getting less than half, they tend to reject. And so in this case, people are both the giver and the receiver are acting irrationally, but that's what the data show. So this is a pattern of data that is sort of similar to what we might see. This is all fake data, but it's a possible pattern we might see. If we look at it, we can tell that the way I've designed it, I've got a balanced design. And having a balanced design is going to be important to test the interactions, because if I don't have a balanced design, then the different ways I type 2 versus type 3 ANOVAs are going to matter a lot. If you look at, let's see, I must have skipped to a different page. Okay, so we can look at what the data look like here. And again, this is fake data, but you can see that if we consider men versus women who are the dictator, deciding how much to give, you might find that if you tell them, oh, the opponent is a male, or you tell them opponent is a female, versus you don't tell them at all, that women overall give more money than men, and men give less money. So there's this main effect of gender here. And regardless of if your partner is a man or a woman, you give about the same amount. Maybe here people give a little more to women than men, but if you don't know the gender, people give a lot less. So this is just a hypothetical amount, and it looks like, for the most part, these are going to be a main effect of gender and a main effect of the gender of the opponent, but no interaction. So to test this, we could look at the main effects only model using, and then but again, this is a type 1 ANOVA. It's going to look at condition in response to the intercept, and then gender in response to condition and gender. And so we might want to do an ANOVA with a capital A. And because it's orthogonal, you can see these sums of squares are all the same. The f values are the same, and the p values are the same. So in this case, it doesn't matter. I could do the interaction model, and we'll get to this later, but you know, what you might want to do just to test these things is look at the Tukey HSD test of this. Tukey HSD for an interaction. We've seen the main effect Tukey HSD before, and here you can see there is no difference between gender here, so these two are no different. There is a difference here between the gender of the dictator, so this difference is significant. And then you can look at all of these and ask for any pairing of these, are they different? And so this doesn't talk about the overall interaction. This just talks about pairs, and you can see that some of these pairs are different and other of these pairs are not different. And you could establish the particular pattern you care about by looking at the Tukey test, post hoc Tukey test. But maybe we want to look at this in terms of the type 2 ANOVA, so we use the CAR library, the capital ANOVA. And here we see condition and gender are both significant, and that interaction, the overall interaction, is not significant. So that tells me a lot more than looking at all of these pairwise differences between possible pairings, because it says, you know what, this and this and this are all the same size. And I don't have to worry about all of the other pairings. Okay. But let's say that, okay, so model, I guess I could just redefine model 1 and model 2. And let's say I wanted to look at model 1, which has this interaction, instead of a type 2 as a type 3 ANOVA. Here's what I was saying before. This is wrong. So in general, this is going to be wrong because the contrasts are not centered and orthogonal. So we want to recode these into ones that are, and we could use contrast poly for each of these. So condition has 3 levels and gender has 2 levels, so we can do that just like we've done in the one-way ANOVA chapter. And we can run this again. So this would be the right way to do the type 3 ANOVA. And now if you look at this, we've got condition and gender is identical. Gender is the gender F test and the condition F test and sum of squares are now different in these cases, and a different amount gets taken up by the intercept. So this type 3, remember, is going to be using a different way of partialing these things out. And especially what it's doing now is testing these after the effect of the interaction has been considered rather than before the effect of the interaction. So it's saying, let's take this interaction into account, and that interaction is going to be this plus this minus this, and the fact that that's small means that, but in a balanced way, the fact that that's small means these will, it's not going to have much of an effect, but it does a slightly different test. We could reset these to treatment contrasts and then create a new data set by resampling these. So if I did this, now we have an unbalanced data set. We have the same number, but we have them divvied up, and this might be more of what you'd expect if you were both randomly sampling men and women on a college campus or in a Mechanical Turk, and then each one of them randomly got one of these 3 other conditions. So if it wasn't designed, this would be a very typical data set you'd have. You'd have different numbers in each of these cases and no way of making it the same. So even though the contrasts here are coded, the fact that we have unbalanced numbers in each cell means that we have an unbalanced design, And now some of these are, it's really going to matter. So here's the interaction model again, with this new data with Ultim 1B. And so here we see no interaction, just like before. And but if we want to do type 3, again, that's not going to be right. So the type 3, it says type 3, but this is not going to be right because my contrasts are not coded properly. And so again, I would have to recode the contrasts using polynomial coding. I could run this again, and here's the right one to test the type 3 ANOVA. Generally, it's what people who build these tools and model them and test them a lot say is that this looks a little difficult to do and it's a little annoying, but generally tools like SAS and SPSS don't do anything reasonable in these cases at all. And so they don't even give you the power to do the right model at all. So it's a little annoying to have to do it. And you say, well, why would I use R when I could use something that does it for me? But generally, a lot of other tools won't do it for you either, and won't give you a way of doing it. Okay, so in this case, we might still do sort of variable selection, and we might say, well, it looks like there was no interaction, so let me just consider the model with just the main effects. And I could look at the type 2 ANOVA model now with just the main effects. And what would happen if I think we can do this? I can do the type 3 ANOVA with no interaction, and you can see that the F values are the same here and here, and the P values are the same. Everything ends up being the same, although it does give me the test for the intercept separately in the type 3 model. So when you don't have interactions, these I think are going to be always the same, even if you've got non-orthogonal, well, even if you've got non-balanced elements in your groups. All right. So next, let's look. So that's the basic approach to looking at interactions with ANOVA models. And you can usually do okay by looking at a type 2 interaction. And then maybe doing the Tukey HSD and Model 1D if you want to know more details like does male differ from female, or does no gender differ from female, or no gender different from male. You could have gone basically back to what we did the first day, though, in these cases, and just done a pairwise t-test. And this is the pairwise t-test that corrects for multiple testing and get the same thing. We get the same results here, but again, this is not necessarily the right thing to do. It's preferable to do the Tukey test over these pairwise t-tests, because in each of these cases, when I'm testing for condition, I'm factoring out the effect of gender. So that's not going to be, in this case, gender, it doesn't know about gender, so the variability of gender is being incorporated. And also the variability of a gender by condition interaction, if it exists, is being incorporated in my residuals. So this could look at each one at a time, but it's generally better to look at this and then do the post hoc tests. Doing this. Okay, so now let's consider a different ultimatum problem where there is an interaction. So again, this is fake data, but this is actually data similar to a study that a student of mine ran. The results are quite similar, where you see a gender by gender interaction. So let's look at what happens here is that, let's consider women first. Women give about the same amount of money to any human of opponent, and they give less money to an unspecified opponent. If you don't know what they are, you maybe think they're a robot and you won't give as much. Men will give more money to a woman and less money to a man, about the same money to a man as they give to an unspecified. So you can see that there's, a gender interaction here. And we'd like to be able to model that in terms of an ANOVA with an interaction. So this should be pretty easy. We can build our model. We could have done an LM or an AOV here with this interaction, and we can just do an ANOVA here. And now we see that condition was significant and gender was significant. These are all, remember, in the context of gender, condition was significant. And in the context of condition, gender was significant. And then in the context of condition and gender, the interaction is significant. If I wanted to do a type 3, I can transform each of these predictors, the contrast related to those, and model that. Here's the type. Well, if you look at the type 2 model, when I change those contrasts is identical. It doesn't change at all. So it wouldn't hurt to use a different coding automatically, but if I use a type 3, now I get different F values because I'm comparing different submodels. It turns out that this one, the interaction is going to be the same in both cases. If you look back at that that lattice picture, this in type 1, type 2, and type 3 ANOVAs is always going to be the same. So the interaction term, testing interaction term, doesn't really depend on this. But these others depend on it, and this would say, well, gender has an effect even when you consider the interaction, which is, it's kind of weird in this case to think about the effect of gender, because what we really have is two different patterns, and so it's like saying on average women give more, but there's an interaction too. So in this case, I don't know if the main effect of gender of the dictator makes a lot of sense, because it's completely explained by the interaction. You could, but what you're asking with this gender effect really is maybe the better thing to do if you're testing the main effect of gender. It's probably better than the type 2 here. The type 2 asks, is there effect of gender once condition is considered? So once I consider this, this, and this, you see, well, there's a small negative effect of gender here, a large positive effect of gender here, and a small negative effect of gender here. So ignoring this condition, is there effect of gender? But really, because it's negative in two of them and positive in the other, really the interaction is what you care about. So if you still, this one is probably more reasonable because you're asking, after you account for this interaction, this positive or negative term, and condition, is there still an effect of gender? And in that case, there is. So it may not make sense, make a lot of sense in either case, but I think the type 3 makes a little more sense in this situation. And then, okay, so that's one approach we can do to sort of make sense of the interactions. We can compare different specific interaction terms. Another thing we can do in this case is do the Tukey test of the model. And now I can say, well, is there a difference here? Well, we can ask if there is a difference there by looking at the second one here is gender, so it's F to M, M to F, and then the first one is let's see, F, oh, this is Okay, so this is hard to piece together. M to F to F is, okay, let me pause and figure this out before I tell you the wrong thing. All right, so each one of these represents a single one of these 6 points. So F to M is condition F, subject M is this one. And if I want to compare F to F, which is condition F, subject F, I could ask, are these two different? And this tells me they are no different. The p-value is 0.5. So these aren't considered different. And I could look at any of these pairs and say, well, how about these? Where do you see the difference in these? And I could use the Tukey test to ask specific questions about individual pairings of this. Okay, so that's another approach to try to understand these interactions. A third approach might be, if you really think that these are two different patterns, I might just do a test of this, or this, or this, which is sort of the same as what we can do with this t-test, but maybe I could do offer by condition for female and offer by condition for male to see if those are different. So another approach is sometimes the advice is to select the subset you care about and do the ANOVA on those. And so here we see the ANOVA of offer by gender for just condition N, which is this. We see it's significant at 0.01. This one is highly significant. And this one is not significant, or at least not significant at 0.05, just like we saw in that Tukey test. Now, the problem with doing this in comparison, this is doing the same 3 tests as I did here, but the problem is it's not taking account of sort of family-wide comparisons, so maybe the Tukey test is a little more safe. These look a little more significant than the Tukey test is, but the Tukey test is saying, well, you could have just had the opportunity to do all of these comparisons. You could have looked at them all, and that's probably 15, 20 different comparisons we have here. So 1 or 2 of them are likely to be significant just by chance. So it's gonna have a more conservative criteria for declaring it significant. Okay, so that's another approach. Let's see. Then I guess the last thing you can do is sometimes you see a 3-way interaction, or an interaction of something with 3 levels is difficult to identify where the difference is. And so you can, but a 2-by-2 interaction is often easy to do. So if I want to see, is there an interaction between just male and female opponent and male and female dictator, that would mean that there's sort of a negative here and a positive here, or a negative here and a flat here. You can do a different subset and look at test the interaction. So here would be an interaction of a subset of these. We sort of have ignored this, and we can say, oh, there's an interaction here, and that's a lot easier to interpret. This might be another approach to sort of understanding and interpreting an interaction. And if I do model tables here, it gives me the specific combinations here that I would need. Finally, another thing you might do is you can build the contrasts yourself. So here's a way of saying, of creating your own contrasts that map onto your hypotheses. And so let's see, this one would say something like, I want to recode condition into these 3 dimensions that say I'm going to look at the difference between these two, that's A. And then B is the interaction between these two. And then C is like this is sort of the effect of the gender of the dictator. And so you could create your own set of contrasts and transforms, and you have to sort of think about exactly how you want to do that. But in this case, we've got these different parts, these different types of conditions that we then contest individually. So sort of flattening it out and partialing out in ways that map directly onto your hypotheses. All right, so that is it for this part of the chapter. We've got one more part of the chapter, which is going to be on effect sizes, that we'll finish up in the next video, and then move ahead to another aspect of interactions, which is the ANOVA. Right.